Welcome to qnawire.
Our objective is to prove that the Wigner Seitz cell for any two-dimensional Bravais lattice is either a hexagon or a rectangle, and to prove that the hexagonal faces of the BCC Wigner Seitz cell are all regular hexagons. First, let's consider a two-dimensional Bravais lattice. A Bravais lattice is a set of points in space such that the surroundings of each point are identical. In 2 dimensions, there are 5 possible Bravais lattices: square, rectangular, centered rectangular, hexagonal, and oblique. 2. The Wigner Seitz cell is a primitive cell that is constructed by drawing lines or planes in 3D that are perpendicular bisectors of the lines connecting a lattice point to its nearest neighbors. The Wigner Seitz cell is the region of space that is closer to the lattice point than to any other lattice point. 3. Now, let's analyze the possible shapes of the Wigner Seitz cell for each of the 5 two-dimensional Bravais lattices. A square lattice, the nearest neighbors are at the corners of a square. The perpendicular bisectors form a square, so the Wigner Seitz cell is a square. The rectangular lattice, the nearest neighbors are at the corners of a rectangle. The perpendicular bisectors form a rectangle, so the Wigner Seitz cell is a rectangle. C-center rectangular lattice, the nearest neighbors are at the corners of a rectangle and at the center of the rectangle. The perpendicular bisectors form a hexagon, so the Wigner Seitz cell is a hexagon. D-hexagonal lattice, the nearest neighbors are at the corners of a hexagon. The perpendicular bisectors form a hexagon, so the Wigner Seitz cell is a hexagon. E-oblique lattice, the nearest neighbors are at the corners of a parallelogram. The perpendicular bisectors form a parallelogram, which can be considered a special case of a rectangle. 4. From the analysis above, we can see that the Wigner Seitz cell for any two-dimensional Bravais lattice is either a hexagon or a rectangle. Now, let's prove that the hexagonal faces of the BCC Wigner Seitz cell are all regular hexagons. 1. In a body-centered cubic BCC lattice, there are lattice points at the corners of a cube and at the center of the cube. 2. The nearest neighbors of the central lattice point are the corner points of the cube. 3. To construct the Wigner Seitz cell, we draw planes that are perpendicular bisectors of the lines connecting the central lattice point to the corner points of the cube. 4. These planes will intersect the faces of the cube along lines that are parallel to the cube edges and halfway between the central lattice point and the corner point. 5. The intersection of these planes with the cube will form a polyhedron with 14 faces, 6 square faces and 8 hexagonal faces. 6. The hexagonal faces are formed by the intersection of 3 planes, each of which is perpendicular to one of the cube edges and passes through the midpoint of the opposite edge. 7. Since the cube is symmetric, all of the hexagonal faces will have the same shape. 8. The hexagonal faces are formed by cutting off the corners of the cube, so each hexagonal face will have equal side lengths equal to half the diagonal of a square face of the cube and equal angles 120 degrees. 9. Therefore, the hexagonal faces of the BCC Wigner Seitz cell are all regular hexagons.